Uh, Good evening, everyone. Is my screen visible and am I audible?
Yes.
Yes.
Okay, thank you. So, let us start today's session. I welcome all of you to the 11th live session of the course Thermodynamics, which is being offered by IIT Delhi. As in for myself, I am a PMRF PhD scholar in the Department of Mechanical Engineering at IIC Bangalore, and uh, I shall be dealing with the live sessions of the course, wherein we shall solve some sample problems from the concepts that were discussed in the previous theory class of the course, so as to help you with the problem solving skills and clear the doubts related to the concepts. Today we shall be uh, discussing on the problems related to the reacting mixtures. So, without any further delay, let us begin with the class with the problems. So, and at any point of time, if there is any doubt, you can just interrupt and ask. Uh, so, the first problem is 1 kilomole of octane is burned with air that contains 20 kilomole of oxygen. Assuming that the products contain only carbon dioxide, water, oxygen, and nitrogen, determine the mole number of each gas in the product and the air fuel ratio for this combustion process. Okay, so basically, what is happening here? So this is a combustion chamber. This is the octane of 1 kilomole, and there is air for the combustion process. Now this air, we will assume that the air is a mixture of oxygen and nitrogen with 71% of nitrogen and 29% of oxygen by volume. Okay, so it is stated that the number of moles of oxygen is 20 kilomole. Okay, so sorry, there was a mistake. So we will assume the air to be having 79% of nitrogen by volume and 21% of oxygen by volume. Okay, so if we take the ratio of nitrogen to oxygen in air, it will come out to be 3.76. That is, for every mole of oxygen in air, there is 3.76 mole of nitrogen in the same air. Okay, so for like 20 kilomole of oxygen, there will be 20 multiplied by 3.76 kilomole of nitrogen in the air that we are using for the combustion. Okay, okay, so the products here are X for carbon dioxide, Y water. Let us assume, so the products are carbon dioxide, water, oxygen and nitrogen. So oxygen and nitrogen. So let this be X, Y, Z and W. Okay. Now essentially nitrogen, although it is present in air, it does not take part in the reaction. Okay, so it acts like an inert gas here. So whatever nitrogen, that is 20 kilomole multiplied by 3.76, 20 multiplied by 3.76 kilomole of nitrogen that was present in the air will be intact after the combustion reaction. So this amount amount of nitrogen will be essentially equal to 20 multiplied by 3.76 kilomole. Okay, now we can write the chemical equation for the combustion reaction as so this is 20 for the, that is 20 moles of oxygen, so it will come with 20 multiplied by 3.76 moles of nitrogen. So this is X moles of carbon dioxide plus Y moles of water plus Z moles of oxygen and W moles of nitrogen. Okay. Now we will do a mass balance of the elements. Okay, so here there is eight atoms, or we can say that if there is 1 kilomole of this, then there will be 8 kilomoles of carbon, and there is x kilomoles of carbon on the right hand side. So for carbon, if we make the balance, then x will come out to be 8. Similarly for hydrogen, if we make the balance, then we can write this twice y equals to 18, which gives that y equals to 9. Now now we are balancing oxygen. Okay, oxygen. So for oxygen it will be twice x plus y plus 2z. Twice x plus y plus twice z is equal to 40. Is equal to 40. Okay. 28 plus 9 plus 2 into z is equal to 40. Plus z is equal to 7.5. And for nitrogen, if we balance it, then W will come out to be 20 into 3.76, that will be 75.2. Okay. Okay, so now so the equation, if we put the values of x, y, z and w in the equation, we will get if the combustion reaction becomes C8H18 plus 20 of oxygen plus 3.76 of nitrogen, that will give 8 of carbon dioxide plus 9 water and 7.5 oxygen plus 75.2 nitrogen. Okay, so this oxygen, 7.5 moles of oxygen that is in the product side, this implies that the entire 20 moles, 20 kilomole of oxygen is not utilized for the combustion. That is, some of the oxygen is remaining as an excess, but there is no carbon monoxide here. That is, the fuel is being burned completely. Okay, so there is complete combustion of the fuel in presence of excess oxygen. So this is basically an excess oxygen. Okay, so if we take basically 7.5 to the left hand side, we'll get 12.5 moles of oxygen would have been sufficient. That is 12.5 mole for the complete combustion of octane. 12.5 moles of oxygen would have been the actual requirement for the complete combustion of this octane fuel. Okay, and that is called the theoretical volume of air, theoretical amount of air. Okay, so here the combustion is taking place at a excess amount of air. Okay, therefore the required number of moles in the product are carbon dioxide 8, hydrogen 9, oxygen 7.5 and nitrogen 75.2. Okay, and the air fuel ratio here is mass of air to mass of fuel. So this is 20 multiplied by 32 plus 3.76 into 28. Okay, this is on a mass basis. So there are 20 moles in total. Of that, 32 is the mass of the oxygen, and 3.76 times there is nitrogen. Okay, and this is 8 multiplied by 12, that is for carbon in the octane, plus 18 multiplied 1, and this is the hydrogen in the octane. So this gives 24.1 kg of air per kg of fuel. Okay, so per kg of fuel, 24.1 kg of air is being burned, and although it is in excess here. Okay, so this is the solution of the problem. If there is any doubt, you can ask. Okay, so if there is no doubt, then I will move on to the next problem. Okay, so moving on to the next problem. Determine the air fuel ratio on both a molar and mass basis for the complete combustion of octane with theoretical amount of air and 150% theoretical amount of air. So the air fuel ratio on a molar basis and mass basis we have to determine with the theoretical amount of air that is for the combustion of octane. What is the air fuel ratio on a molar basis and a mass basis? In the previous question we have only determined the air fuel ratio on a mass basis. Okay, now we will determine on both mass basis and molar basis with the theoretical amount of air and then 150% theoretical air, that is 50% excess air. Okay. So let us start. Now for the combustion of mm, now for the combustion of the octane with the theoretical amount of air, the product should not contain any value of oxygen. That is, the entire oxygen in the air should be used up. Okay, so so we can write it as just let me write it down. For the combustion, or we can write complete combustion octane with theoretical air there will not be any oxygen or carbon monoxide in the product. Okay, see, the carbon monoxide carbon monoxide is present in the product only when that is incomplete combustion. That is, carbon monoxide is essentially a product of incomplete combustion of the fuel. And so since we have uh, written complete combustion of fuel, there will be no carbon monoxide in the product. First, second is the oxygen. And for oxygen, since we are using theoretical amount of oxygen, that means that the entire amount of oxygen in the air will be used up. Okay, so there will be no oxygen in the product. Okay, and the product will contain only you can just write the equation directly. And the product will essentially contain only nitrogen, that is as inert gas, and that is it does not take part in reaction, and carbon dioxide and water. So this C8H18 plus, let there be for theoretical amount of air, let the number of moles be A theoretical, and it is oxygen plus 3.76 times of nitrogen. It gives see, we have already shown in the previous one how this balance happens. So basically 8 C8H18 will give rise to uh, 8 moles of carbon dioxide. Although we can write it here as well, but we could have also written it directly, like B CO2 plus C H2O plus D nitrogen. Okay, so B will basically be 8 if we make a mass conservation of the elements. Conservation from the conservation of carbon, B is equal to 8. From the conservation of hydrogen, twice of C equals to 18, that is C equals to 9. From the conservation of oxygen, okay, 2B plus C is equal to twice of A theoretical. Okay, this implies A theoretical is equal to 2 into 8 plus 9 by 2, that is 12.5. Okay, and for nitrogen, D is equal to 3.76 A theoretical. So this is 3.76 into 12.5, that is 47. Okay, so basically there will be 47 moles of nitrogen. So the theoretical with the theoretical air, the equation, combustion equation will become C8H18 plus 12.5 oxygen plus 3.76 nitrogen, 8 carbon dioxide plus 9 water plus 47 nitrogen. Now the air fuel ratio on a molar basis. So there is 1 mole of fuel and the number of moles of oxygen is 12.5 and the number of moles of nitrogen is 12.5 multiplied by 3.76. Okay, so we can write it as 12.5 into 1 plus 12.5 into 3.76 by 1. So the air fuel ratio in this will be 59.5 kilomole of air per kilomole of fuel. Okay, and air fuel ratio on a mass basis. 12.5 into, this is mass of oxygen is 32 plus 3.76 into mass of nitrogen is 28 by 8 into 12 plus 18 into 1. So this is 15.05 kg air per kg of fuel. Okay, so we have determined the air fuel ratio on a mass and molar basis for theoretical amount of air. Now if we um, now with 150% theoretical air, if we do the conversion, that is 50% of excess, that is 15% of excess, that is 1.5 times 12.5 oxygen plus 3.76 nitrogen, that will give B carbon dioxide plus C water plus D nitrogen plus E oxygen. Essentially, see, this will be the same as before, so we can write it as that B is equal to 8 and C equals to 9. If we do a conservation of um, oxygen, then we can write it as E equals to 1.5 into 12.5, that is 1.5 into 12.5, not this one exactly, E plus, from here it is B plus C by 2, that is equal to 1.5 into 12.5. Okay, so from here we can write E to be 6.25, that is 6.25 moles of oxygen is in excess here, and nitrogen, if we do, then D equals to 1.5 into 12.5 into 3.76. Okay, so D will come out to be 70.5. Therefore, with 150% excess air, the combustion reaction becomes C8H18 plus 1.5 into 12.5 of oxygen plus 3.76 of nitrogen, that will give 8 carbon dioxide plus 9 water plus 70.5 nitrogen plus 6.25 oxygen. Therefore, the air-fuel ratio on a mass basis, air-fuel in a first molar basis, equal to 1.5 to 12.5 to 1 plus 3.76 by 1. So this will basically be 89.25 per kilomole of fuel, and this value is essentially just 1.5 times of what we had obtained previously, that is 59.5. Okay, also the air fuel ratio on mass basis will also be the same, that is 1.5 times of what was previously. So this is 22.58 kg air. Okay, So from this we can understand that we can directly, if we know the theoretical airfield ratio, airfield ratio on mass or molar basis, then we can directly use the suppose we have been told that we are using 200% of the exact of the theoretical air, then the airfield ratio will become like 200% of the of what we find from the um, theoretical air calculation. So this is just a that is they vary at the with the same factor. Okay. Okay, so uh, mm, if there is any doubt you can ask, else we will move on to the next problem. Okay, so I'm taking that there is no doubt. uh, then we are moving on to the next problem. Now a certain natural gas has the following volumetric analysis, that is 72% of methane, 9% of hydrogen, 14% of nitrogen, 2% of oxygen, and 3% of carbon dioxide. Okay, this is the natural gas, and this gas is now burned with stoichiometric amount of air that enters the combustion chamber at 20 degrees Celsius, 1 atmospheric pressure, and 80% relative humidity. Assume complete combustion and a total pressure of 1 atmosphere. Determine the dew point of the products. Okay, so what is happening is this is a combustion chamber.
Battery is discharging.
In it we are giving a natural gas which composition is 72% methane, 9% hydrogen, 14% nitrogen, 2% oxygen, and 3% carbon dioxide. And along with it there is air, uh, stoichiometric amount, that is theoretical amount of air that is required for the burning, such that there is no excess oxygen in the in the product. Okay, and it is supplied at 20 degrees Celsius, 1 atmospheric pressure, and relative humidity is 80%. Okay, and we will get the products. What we will get the products as since there is we are assuming that there is complete combustion. Okay, we are assuming that there is complete combustion, so there will be only carbon dioxide, water, and the unreacted nitrogen. So X, Y, and Z. So let the reaction be, we are assuming that we are taking 1 kilomole of this product of this natural gas. Okay, we are taking 1 kilomole of this natural gas. Okay, in that case, the considering 1 kilomole of the fuel. Okay, we can write the fuel to be now 0.72. This is 72% methane, right? So 0.72 CH4 plus 0.09 hydrogen plus 0.14 nitrogen plus 0.02 oxygen plus 0.03 carbon dioxide, plus let there be for the the stoichiometric amount be A, corresponding to this fuel. So this is oxygen plus 3.76 nitrogen, and a complete combustion of the product will give X carbon dioxide plus Y water plus Z nitrogen. Okay, now if we do a conservation of the elements, from the conservation of carbon we'll get 0.72 plus 0.03 is equal to X, implies X is equal to 0.75. With hydrogen, 2 multiplied by 0.09 plus 4 multiplied by 0.72, this is equal to 2 twice Y. This implies Y is equal to 1.53. Okay. Then for oxygen, it is 0.02 into 2 plus 0.03 into 2 plus twice A. Okay, so this will give the value to be twice X plus Y. How? Twice X plus Y. Okay, so the value of A, you are looking at the value of X and Y, so the value of A is unknown, so and the value of A comes out to be 1.465. And for nitrogen, if we do, then 0.14 into 2 plus A into 2 into 3.76, this is equal to 2 into Z. This implies Z is equal to 5.648. Okay, therefore now in this we are considering only dry air first. Okay, in this we have written we are considering that only air with oxygen and nitrogen is coming, but in actually that is 80% of relative humidity. That is, there will also be some amount of water vapor present in the air. So we have not considered that. We have already considered that the reaction with the dry air. Okay. Now now we will modify the equation for the including the moisture as well. Okay, now this air has a relative humidity air enters at a relative humidity of 80%. Okay, and at 20 degrees Celsius. 20 degrees Celsius. Now at 20 degrees Celsius, the saturation pressure of water is equal to 2.3392 kPa. Therefore, the vapor pressure in the air will be equal to 0.8 into 2.3392. Okay, so this is equal to 1.871 kPa. That is 1 atmospheric pressure. Okay, that is 101.325 kPa. Uh, this pressure 1.871 is of the vapor. Okay. Now the total number of moles of air is what? A is the total number of moles of dry air. Number of moles in dry air. This is equal to 1.465 into 1 plus 3.76. So it comes out to be 6.97 kilomole. Okay, and pressure of dry air is P minus PV. That is 101.325 minus 1.871. So this comes out to be minus 1.871, 99.454 kPa. Okay, considering both air and the moisture, that is the water vapor, as ideal gases, we can write this equation for considering both air and water vapor as ideal gases. We can write that the pressure will be proportional to the number of moles. Okay, therefore PV by PA will be equal to number of moles of vapor by number of moles of air. This implies for this many moles of air, dry air, the number of moles of the vapor in the same condition will be this one. Okay, so putting the values 1.871 by this is 99.454 multiplied by 6.97, so this comes out to be 0.1311 kilomole. Okay, therefore moist air, which is contains dry air plus water vapor, so dry air will be 6.97 kilomoles and this is 0.1311 kilomole. That will be the total number of moles of the moist air. Now therefore the balanced combustion equation will be 0.72 CH4 plus 0.09 hydrogen plus 0.14 nitrogen plus 0.02 oxygen plus 0.03 carbon dioxide plus 1.465 oxygen plus 3.76 nitrogen plus 0.1311 water. Okay, these combined gives a product 0.75 carbon dioxide plus 1.53 plus 0.1311 water. So with the dry air it was 1.53 kilomoles of water. Now the moisture, this moisture will also remain unreactive. So it will just turn up at the as a product in the reaction. So this will be added 0.1311, that is a fraction of water vapor will just get added plus 5.648 nitrogen. Okay, so this is basically 0.75 carbon dioxide plus 1.661 water 1.661 water plus 5.648 nitrogen. So this is a balanced combustion reaction. Now the total number of moles in the product is equal to 0.75 plus 1.661 plus 5.648. So this is basically 8.059 kilomole. And number of moles of the vapor only. This is the number of moles of product, and the number of moles of vapor only is 1.661. So this vapor will basically condense, and that at the temperature at which this starts condensing will give the dew point temperature of the entire product mixture. Okay, therefore again considering both vapor and the gases as the ideal gases, so PV by P total is equal to NV by N product. This implies the partial pressure will be this. So 1.661 by 8.059 multiplied by 101.325. This is 20.88 kPa, which is equal to the partial pressure of water vapor in the combustion product. And corresponding to saturation pressure of 20.88 kPa, the saturation temperature is 60.9 degrees Celsius. Okay, therefore dew point of the products of combustion is 60.9 degrees Celsius. Okay, so I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so I am taking that there is no doubt. So we will move on to the next problem now. Ethane is burnt with 20% excess air during a combustion process. Assuming complete combustion and a total pressure of 100 kPa, determine the air-fuel ratio, the dew point temperature of the product. Mm, mm. So ethane is burnt with 20% of excess air, and there is complete combustion, that is there is no carbon monoxide present in the product, and there is an excess of air, so there will be oxygen present in the product, and a total pressure of 100 kPa. Determine the air-fuel ratio and the dew point temperature of the mm, determine the air-fuel ratio and the dew point temperature of the products. Okay, so the fuel ethane is completely burned, okay, with excess air. So does there will there is no there will not be any carbon monoxide in the product, but oxygen will be present in the product. Since it is burnt with excess of oxygen, okay, excess of air. So the combustion reaction, let us write the combustion reaction. C2H6 plus 1.2 A oxygen plus 3.76 nitrogen, twice CO2 plus 3H2O plus 0.2. Why 0.2 A oxygen? Because the excess from let A be the theoretical one, okay, and 0.2 A is what we are giving excess, that is 20% excess. So 20% excess of oxygen will remain unreacted in the product, okay. So 0.2 AO2 plus 1.2 into 3.76 A nitrogen, okay. Now by mass balance we can write 2 into 1.2 is equal to 2, this is 4 plus 3 plus 0.2 into 2. Okay, that is twice A is equal to 7 or A is equal to 3.5. Okay, so we can write the equation to be C2H6 plus 4.2 oxygen plus 3.76 nitrogen, that will give 2 CO2 plus 3H2O plus 0.7 oxygen plus 15.79 nitrogen. Now the air fuel ratio on mass basis is mass of air by the mass of fuel. So this is 4.2 to 32 plus 3.76 into 28 divided by 2 into 12 plus 6. This is 19.22 kg air per kg of fuel. Okay. Now we also have to determine what is the dew point temperature of the product. Okay. So for dew point, we have to find the we have to do what fraction of water in the product. That is, what is the fraction of water in the product. Okay, for that, the dew point of the product dew point of the product correspond to the temperature correspond to the temperature at which water vapor in the product starts condensing. Okay, so here the number of moles of vapor is 3, right? It is 3 moles of vapor, kilomoles of vapor, and the number of moles of product is 2 plus 3 plus 0.7 plus 15.79. So this is basically 21.49 kilomole. Okay. Now, therefore, PV by P total is NV by NP. That is a total and considering both the water vapor and the other gases to be ideal gases. Okay. This implies PV is equal to 3 by 21.49 into 1000. Sorry, 100. 100 kPa. So it comes out to be 13.96 kPa, corresponding to P saturation of water equals to 13.96 kPa. The T saturation, that is the saturation temperature, is 52.3 degrees Celsius. Therefore, dew point of the products is 52.3 degrees Celsius. Okay. So I hope it is clear to everybody. If there is any doubt, you can ask. Okay, I am taking that there is no doubt, so we will move on to the next problem. So let us move on to the next problem. A natural gas has the following molar analysis. CH4, that is methane 80.62%, ethane 5.41%, and propane 1.87%, and butane 1.60%, nitrogen 10.50%. This gas is burnt with dry air, okay, giving products having a molar analysis on a dry basis. Right, that is, we are not considering the moisture present in the air. And on a dry basis, there is carbon dioxide 7.8%, carbon monoxide 0.2%, oxygen 7%, and nitrogen 85%. Okay, this is on a dry basis. There will be still water present in the product. Determine the air fuel ratio on a molar basis, assuming ideal gas behavior for the fuel mixture. Determine the amount of products in the kilomole that would be formed from 100 meter cube of the fuel mixture at 300 Kelvin and 1 bar. Determine the percent of theoretical air. Okay. Okay. So here the fuel mixture. So this fuel mixture, that is a natural gas mixture, in all of these gases like methane, ethane, propane, butane, and nitrogen. All of these are individually considered as ideal gases. Then this mixture of gases will also be an ideal gas. Therefore, this, that is a fuel mixture, is modeled as ideal gas. Okay. Now, in the combustion air, each mole of oxygen is accompanied by 3.76 moles of nitrogen, which is inert. Okay. So the combustion reaction, let us write the combustion reaction. Zero point 0.8062 methane. Why 0.8062? We are assuming that there is a net 1 kilomole of the natural gas. Okay, so in that case, the methane being 80.62 on a molar basis, it will be 0.8062 kilomoles of methane. Okay. Plus 0.0541 is 5.41% of ethane, plus 0.0187 of propane, plus 0.0160 of propane, plus 0.1050 of nitrogen. So along with the air that we are using, this nitrogen will also remain as inert. Now we are saying that the gas is burnt with dry air. That is, there is no moisture. There is no moisture at all. In the previous problem, we had considered dry air initially, and then we had included the moisture separately. But here it is said that it only burns dry air. Okay, so there will be no question of moisture. That is, moisture is not present. Okay, and the products be, here there will be b kilomoles of entire thing. This giving products having a molar basis, molar analysis on a dry basis. So what does molar analysis on a dry basis means? That is, if we consider the dry fractions in the moisture, that is a dry constituents in the moisture in the product, dry constituents in the product. If we consider the dry constituents in the product, then on a molar basis, that is per kilomole of the dry products, the carbon dioxide is 7.8%, the carbon monoxide is 0.2%, the oxygen is 7%, and the nitrogen is 85%. In addition to these, there will be moisture which is formed from the reaction. So the please try to understand the difference between the molar analysis on a dry basis and dry air. So in dry air there will be no moisture present, but on dry basis, on when the analysis is done on a dry basis, we are not considering the moisture, but the moisture will actually be present. That has to be included separately. Okay. Now this is 0.078 of carbon dioxide plus 0.002 of carbon monoxide plus 0.07 of oxygen plus 0.85 of nitrogen. Okay, so this is on a per kilomole basis, so multiplied by B, assuming that B kilomoles of the dry gaseous products are produced, plus the moisture. Now we are including separately as C moles of water. Okay, that is per kilomole of fuel that is, therefore, that is for per kilomole of fuel, the product contains product contains B kilomole of dry products and C kilomole of water vapor, that is the moisture. Okay, so till now if it is clear, then it is fine. Otherwise, if there is any doubt, you can ask. So I am taking that there is no doubt. Now conservation of mass applied to the elements. Okay, this is 0.8062 plus 0.0541 into 2 plus 0.0187 into 3 plus 0.0160 into 4 equals to B into 0.078 plus 0.02, sorry, 0.0002B. This implies B is equal to 12.931. Okay. Okay. Now for hydrogen, if we do, then 4 into 0.8062 plus 6 into 0.0541 plus 8 into 0.0187 plus 10 into 0.0160 is equal to 2C. This implies C is equal to 1.93. And for oxygen, if we do, then twice A is equal to 2B. Okay, for oxygen, if we balance it, then twice A is equal to 2B plus 0.002 B plus 2 into 0.07 B plus C. Plus 2 into B into 0.07. Okay, so the value of A comes out to be 2.892. Okay, therefore the balanced equation for the combustion 0.8062 CH4 plus 0.0541 C2H6 plus 0.0187 C3H8 plus 0.0160 C4H10 plus 0.1050 nitrogen plus 2.892 oxygen plus 3.76 nitrogen is 12.931. 0.078 carbon dioxide plus 0.002 carbon monoxide plus 0.07 oxygen uh, 0.07 oxygen plus 0.85 nitrogen plus 1.93 water. So in excess of the dry products in the dry products of the combustion, there will be 1.93 kilomole of water, that is moisture in the product. Okay. Now air fuel ratio on a molar basis. Air fuel ratio on a molar basis equal to 2.892 into 1 plus 3.76. So this will come out to be 13.77 kilomole air per kilomole of fuel. Now the second part, we have to determine uh, what is the assuming ideal gas behavior for the fuel mixture. We have to determine the amount of products in kilomole that would be formed from 100 meter cube of fuel mixture. Okay, so the volume of the fuel mixture is given at 300 Kelvin and 1 bar pressure. So corresponding to that, what is the amount of product that will be formed? Okay, now the number of moles of fuel in 100 meter cube at 300 Kelvin and 1 bar and 1 bar is PV by universal gas constant into T. So this P is 1 bar, that is 10 to the power 5 into V is 100 meter cube by 8 0.314 into 300. Okay. Let me do one thing. See, this is in kilojoule per kilomole Kelvin, right? So this we will write it as in kilopascal. So pressure is 1 bar, that is 100 kilopascal. So that will give 4.01 kilomole. Okay. Okay. So now since from the previous balanced combustion reaction, we have seen that 1 kilomole of the fuel, this is total fuel, gives 12.93 plus 1.93 moles of the product. Okay, therefore it will just be a multiple by this factor 4.01 kilomole. Okay, now since 1 kilomole of fuel gives 12.93 plus 12.91 plus 1.93, that is 14.861 kilomole of product. Okay, therefore 100 meter cube of fuel, that is equivalent to 4.01 kilomole of fuel, gives 14.861 multiplied by 4.01, that is 59.59 kilomole of product. Okay. Now for the theoretical air percent, so this will be the kilomole of product present in due to 100 meter cube of fuel. Okay. Now for the theoretical, we have to determine what is the percent of theoretical air, that is what percent of theoretical air basically is being used in this combustion. Okay. Like initially we had solved problems where 20% of excess air is used, or we have solved problems where some 30% of theoretical air is used, or 150%. So now here we have to determine what is the this air volume that we have used. We have determined, right, the value of A. The value of A we have found out to be 2.892. So this volume, this amount of air is what fraction of the theoretical air, and it will obviously be an excess of the theoretical air because there is excess of oxygen present in the product. Also as excess of oxygen present in the product, so this will be an excess, and that is it will be higher than the theoretical amount of air that would have been required. So first we will find out the theoretical amount of air to be required. We can find out by writing this equation again and solving it, or we can do one thing, is that we can consider that So there is an excess of oxygen on the left hand side, which becomes the excess oxygen on the right hand side as a product, right? So if we subtract this fraction of oxygen in the product from the total amount of oxygen in the reactant, then we will get the actual amount of oxygen that reacts in this case. Okay. And the remaining is actually the excess oxygen. Okay. So we can write it as for theoretical combustion, there is no oxygen in the product. Therefore, the number of moles of oxygen in reaction will be, that is on the reactant side, will be 2.892 minus 12.931 into 0.07. Okay, this comes out to be 1.987 kilomole. Okay, so from 2.892, this 1.987 kilomole of oxygen is actually utilized in the reaction, giving rise to the products that we get here as in carbon dioxide, in carbon monoxide and water, and the remaining uh, fraction is remaining as unreacted oxygen. Okay. Therefore, the theoretical air-fuel ratio is 1.987 to 1 plus 3.76 by 1. Why? Because 1.987 kilomoles of oxygen will be required for exact theoretical combustion, that is for the oxygen to be completely utilized. Okay, so accordingly the moles of oxygen will be 3.76 times of that. So in molar basis, this will be the air fuel ratio, which comes out to be 9.46 kilomole air per kilomole of fuel. Okay. Now, therefore, percent theoretical air is 13.77 by 9.46, which is equal to 1.45, that is 145%. So 145% of the theoretical air was actually being utilized in the combustion process here. That is 45% excess air is being used. Okay, and this 45% excess air comes as this one, oxygen 7% in the analysis. Okay. Mm, so I hope it is clear to everybody. If there is any doubt in any portion of this, you can ask. So these problems are very much useful when we go for the solution of IC engine questions, or for when we analyze the IC engines which are used in motor vehicles. So these reactions These concepts are I mean, they come quite handy when you are using when you are trying to analyze the SNGs, and hence the analysis of the motor vehicles. So if there is any doubt in any section of this, please do ask. Sorry about that. Uh, so if there is no doubt in the problem that we just solved, we will move on to the next problem. Okay, so let us move on to the next problem. So, octane is burnt with dry air. The volumetric analysis of the products on a dry basis is carbon dioxide is 10.02%. Uh, mm, 10.02%, oxygen is 5.62%, and carbon monoxide is 0.88%, and nitrogen is 83.48%. And so for the volumetric analysis, determine the air fuel ratio, the percentage of theoretical air use, and the amount of water that condenses as the products are cooled to 25 degrees Celsius at 100 kPa. Okay, so the combustion gases are ideal gases. The combustion gases are ideal gases. Okay, then the total number of moles of the dry let the so this is the product on a dry basis, right? That is, it does not include the water moisture content here. So let the total number of moles of dry products be 100 kilomole. Okay, instead of 1 kilomole in everything, we are now taking 100 kilomole this time. So let X be the kilomoles of the fuel that is being burned with a kilomole of air to give 10.02 of CO2 plus 5.62 oxygen plus 0.88 carbon monoxide plus 0.8348 nitrogen. Okay, and this is on a dry basis, so there will be an additional of moisture content, that is BH2O. Okay, by conservation of mass or the number of moles, we can say by conservation of mass of elements. Okay, now for nitrogen, if we do, then 3.76 A is equal to 83.48, which implies A is 22.20. For carbon, if we do, 8x is equal to 10.02 plus 0.88. This implies x is equal to 1.36. For hydrogen, if we take 18x is equal to 2b, which implies b is equal to 12.24. And oxygen, for oxygen, if we take, then this is A is equal to 10.02. See, A, we are taking oxygen total, mean O2. Okay, so A, this is 10.02 O2 plus 5.62 O2 plus this will be 0.88 O, so this is 0.44 O2, 0.44 O2 plus B. Okay, This implies B is equal to 12.24. So it is like we have found B is equal to 12.24 from this as well as this, so it is balanced. Okay, now the balanced reaction for the combustion is 1.36 C8H18 plus 22.2 oxygen plus 3.76 nitrogen. It gives 10.02 carbon dioxide plus 0.88 carbon monoxide plus 5.62 oxygen plus 83.48 nitrogen plus 12.24 water. Okay, now per mole of the fuel, so this is like 1.36 kilomole of fuel is used, therefore per mole of the fuel, per kilomole of fuel, the equation becomes, so this is, we will just divide all the terms by 1.36. Okay, so it is C8H18 plus 16.32 oxygen plus 3.76 nitrogen. It will give 7.37 carbon dioxide plus 0.65 carbon monoxide plus 4.13 oxygen plus 61.38 nitrogen plus 9 water. Okay, therefore the air fuel ratio on mass basis is 16.32 32 plus 3.76 into 28 divided by 8 into 12, this is 8 into 12 plus 18 into 1, 18 into 1, this is 16.32 32 plus 3.76 28, so this is equal to 19.65 kg air per kg of fuel. So this is the air fuel ratio on a mass basis. Now considering the theoretical amount of air for combustion,
Battery is charging.
and we are also assuming that there is complete combustion. Okay, let me write here complete combustion. There is no excess oxygen and carbon monoxide in product. Okay, Therefore, C8H18 plus A theoretical oxygen plus 3.76 nitrogen will give 8 carbon dioxide plus 9 water plus 3.76 ATH nitrogen. So twice ATH is equal to 2 into 8 plus 9, that is, we have already determined this to be 12.5 for this particular gas, that is octet. Therefore, the theoretical combustion equation becomes C8H18 plus 12.5 oxygen plus 3.76 nitrogen, okay, gives 8 carbon dioxide plus 9 water, okay, plus 47 into. Therefore, percentage theoretical air in air actual by number of moles of air in theoretical. So this is 16.32 by 12.5 is 131%. Okay, so that is 131% of the theoretical air is being used for the actual combustion process here. That is, there is an excess of 31% of air for the combustion process. Now the last part, we have to determine what is the amount of water that condenses as the products are cooled to 25 degrees Celsius. Okay, so we are assuming that the dew point of these gaseous products, all the gaseous products that are formed, that combined dew point of the mixture will be greater than 25 degrees Celsius, such that when they are cooled to 25 degrees Celsius at 1 atmospheric pressure, there will be some condensation of water. Okay, we are assuming that the dew point of gaseous products is greater than 25 degrees Celsius, so that when cooled to 25 degrees Celsius, some water condenses. Let Nw kilomole of water condenses. Okay. Now the saturation pressure of water at 25 degrees Celsius is 3.1698 kPa, and for 1 kilomole of fuel, 7.37 plus 0.65 plus 4.13 plus 61.38 plus 9 is equal to 82.53 kilomole of gaseous products are formed. Including 9 kilomole of water vapor. Okay. we have assumed that 9 Nw is a kilomole of water that condenses. Therefore, number of moles of water after condensation, moles of gaseous, okay, is 9 minus Nw, and number of moles number of moles of gaseous products after condensation, this is Nv, and this is Np is 82.53 minus Nw. Okay, therefore Nv by Np is equal to Pv by P. This implies Nv is equal to Pv, that is 3.1698 by 100 into Np. This implies Nv is 9 minus Nw is 0.031698 into 82.53 minus Nw. Therefore, Nw is 6.59. Therefore, 6.59 kilomole of water condenses, which is 6.59 by 9 is 73.2% of the total vapor present. Okay, so 6.5 kilomole of water basically condenses. So I hope it is clear to everybody. If there is any doubt, you can ask. So if there is no doubt, we will move on to the last problem for today. That is a problem involving the enthalpy of combustion and enthalpy of formation. Okay, so in this, so like in the previous problems where we have seen that there is a combustion basically. Okay, so when this combustion happens, all of these products with respect to some standard state, their enthalpy values will be either greater than that standard state or less than that standard state. Depending on that, there will be the formation of this product will require some heat addition or some heat rejection. Okay, so what is the enthalpy of formation? It is the enthalpy of formation. We can just say that the enthalpy of formation is basically the enthalpy of product at a enthalpy of any particular substance at a specified state because of its chemical composition. Okay, so like the enthalpy of this carbon dioxide, so the enthalpy of this carbon dioxide at the specified state, let it be like 100 kPa and 25 degrees Celsius, that at 100 kPa and 25 degrees Celsius the enthalpy of formation of carbon dioxide will be the enthalpy of this carbon dioxide at this specified state due to this chemical composition, that the carbon and oxygen are linked together in this manner. That is why what will be the enthalpy with respect to some standard state. So what is the standard state? The standard state is taken as that at 25 degrees Celsius and 1 atmospheric pressure, all the stable elements such as this nitrogen, the oxygen, the carbon and hydrogen, the elements like this have zero enthalpy. This is what we have taken as a scale. Okay, so with respect to this, for any product to form from any of these stable elements, what is the enthalpy uh, for the formation? That is, if carbon and oxygen are reacting to form carbon dioxide, then what will be the enthalpy for that? So this can be determined like if carbon and oxygen are reacting to form carbon dioxide, then there will be a release of 393520 kilojoule of heat per kilomole of the carbon dioxide produced. Okay, so this will be since it is a heat released, so this will be denoted as minus. So minus 393520 kilojoule per kilomole is the enthalpy of formation of carbon dioxide at this specified state of 100 kPa and 25 degrees Celsius. This minus and this value is totally determined with respect to the assumption that at 25 degrees Celsius and 100 kilopascal, the stable elements like carbon, hydrogen, oxygen and nitrogen, they have zero enthalpy of formation. And for carbon, since it exists at many different states, so the graphite is taken as a stable form for this. Okay, so and so for all these products, for all the products for all the components in the product side and all the components on the reactant side, there will be some enthalpy of formation. Okay, so the enthalpy of the total enthalpy of the products minus the total enthalpy of the the total enthalpy of formation of the products minus total enthalpy of formation of the reactants will give the enthalpy of combustion. Okay, so what do we need to do here? So the combustion reaction, we are now using theoretical air only. The combustion reaction using theoretical air is theoretical amount of air. Okay, theoretical amount of air is C8H18. Okay, plus let it this be a theoretical, which is close to like what we have determined 12.5. This is nearly equal to 12.5. Oxygen plus 3.76 nitrogen. Okay, it gives 8 carbon dioxide plus 9 water plus 3.76 a theoretical nitrogen. Okay, and this is in the liquid phase. It has been mentioned. Assume that the water it product is in liquid form. Now for the stable elements, like oxygen, hydrogen, nitrogen, carbon, at 1 atmospheric pressure and 25 degrees Celsius, the enthalpy of formation is 0. Is 0. Okay, therefore enthalpy of combustion is the enthalpy of formation of the products minus enthalpy of formation of the reactants. Okay, that is, it can be written as sum of NP HFP, which is for the individual component, the enthalpy of formation per mole of that component multiplied by the number of moles of that component, minus for same for the reactants. Okay, so in the product, nitrogen has an enthalpy of formation of 0, so only carbon dioxide and liquid water will be available. So number of moles and enthalpy of formation, molar enthalpy of formation of carbon dioxide multiplied plus this one for nitrogen water, this is the number of moles number of moles into HF naught bar for water, that is in essentially in liquid phase. Okay, so minus plus nitrogen will be 0, so we are not writing that. Minus for in a product that is oxygen and nitrogen again, so oxygen is also 0, nitrogen is also 0, so that will be only the liquid octane, that is moles into HF, sorry, HF naught for liquid octane, that is C8H18. Okay, so all these values basically are available in any standard textbook for the enthalpy of formation data. So 8 multiplied by minus 393520 plus 9 into minus 285,830 minus 1 into minus 249,950. So this value has been taken from a standard textbook, so you can also use a standard textbook data in a standard table data for the enthalpy of formation of carbon dioxide, liquid water and octane. Okay, so this comes out to be minus 547,100 kilojoule per kilomole of octane. And if we put the molar mass of octane and divide it, then we can get this will be 47891 kilojoule per kg of octane. Okay, so the enthalpy of combustion of octane is this. Okay, so I hope it is clear to everybody. If there is any doubt, you can ask, else we will close today's session. Okay, so I'm taking that there is no doubt. So, and thank you for joining. Please attend the next session on next Friday from 6 to 8 p.m. Thank you.